Forward differences for a given sequence Pn n is equal to 0 to infinite. The forward difference denoted as delta Pn is defined by delta Pn is equal to Pn plus 1 minus Pn for all n greater than or equal to 0. So this sequence can be imagined as the sequence of roots even. So if Pn plus 1 is the improved root and Pn is the previous root, so we can say that the difference of the roots are even Pn can be a polynomial of degree n, and Pn plus 1 can be a polynomial of degree n plus 1. So higher powers of this forward difference can be calculated recursively as follows. For example, so if we want to calculate the second order forward difference of this polynomial, we need to operate another times this forward difference on both sides. So we apply the forward difference up to k times, we will have this delta k Pn is equal to delta into delta k minus 1. There should be a close bracket here. So Pn for all k greater than or equal to 2, because if you take the value of k less than 2, for example, if k is equal to 1, then 1 minus 1 will be equal to 0, and delta power 0 is considered to be 1. So that's why we should keep in mind that k must be greater than or equal to 2. For small positive number h, delta can also be written as, so here we can introduce the small positive number h to simplify the Newton's interpolating polynomial. So delta can also be written as delta f of x is equal to f of x plus h minus x. So just imagine x is a point on the x-axis and x plus h is a small increment in the point x, and it will give the next point 2x. So it is easy to understand that delta f of x is equal to f of x plus h minus f of x, which is called first order forward difference. So to define the second order forward difference can be computed as, so just apply this delta on both sides. So on the left hand side, delta into delta f of x can be written as delta square f of x, or we can write delta multiplied by delta f of x is equal to, on the right side, this delta f of x plus h minus f of x. So here, if you note that inside the brackets, this part f of x plus h minus f of x is actually this delta f of x. So if we apply again the delta on this delta f of x, so we will have delta f of x plus h minus delta f of x. So because delta is a linear operator, so it can be operated inside the brackets. Okay, so, and if you observe, delta f of x is equal to f of x plus h, this one, minus f of x. So this term is the similar as we have here, that f of x plus h minus f of x. So this is delta f of x, and if we want to calculate delta f of x plus h, then f of x plus 2h minus f of x plus h. So we can simplify this. The two terms can be added, so minus 2f of x plus h plus f of x. So here f of x plus 2h. Similarly, we can compute delta of order 3. So delta cube f of x can be written as f of x plus 3h minus 3 f of x plus 2h plus 3f of x plus h minus f of x. So if we continue in this way, we can have a general formula like delta per k, Pn is equal to delta into delta k minus 1 Pn. And now what will happen to the Newton's forward difference interpolating polynomial can be written as the Newton's forward difference polynomial or formula can be constructed by using this forward difference operators del. First forward difference is defined as below, and so here if you recall the definition of first divided difference formula. So what is the first divided difference formula? It means the zeroth divided difference f of x1 minus f of x naught divided by x1 minus x naught. So here x1 minus x naught is a small increment h. So that is why we can write here 1 over h f of x1 minus f of x naught is equal to 1 over h delta f of x naught, because if we just go to the definition of delta f of x, so just we need to replace this x with x naught. So then we will have this f of x1 minus f of x naught is equal to 1 over h delta f of x naught. So next, if we want to compute the second forward difference, which can be calculated as, so to compute the second forward difference, we need 3 points, x0, x1, and x2. And here we make use of the second divided difference formula, and we will have 1 over 2h delta f of x1 minus delta f of x0 over h. This h will be multiplied by the h outside of the brackets, and we will have this h square. So 1 over 2h square into delta square f of x naught. In general, we can write this f of x naught x1 so on xk is equal to the formula in the kth form, that 1 over k factorial and h per k delta per k f of x naught. So what is the advantage of this forward difference, using forward difference? Just imagine that here we need only one point, which is x naught, and we will calculate the value of the function at x naught. So here again at x naught, again at x naught. So it is easy to generalize. Just observe this term. So here is delta square and here is h square. So these two parts are the same. So it means we can write even delta k and h power k. Similarly, this 2 factorial is also equal to the power. So here we can write this k factorial. So it's not difficult to generalize this forward differences. Okay, now recall Newton's divided difference interpolating polynomial. So we can rewrite this polynomial. Uh, Also, we can, if we want to see this polynomial, what was written in the previous lecture, so 5.14 is the same as. So Pn of x, f of x naught plus f of x naught x1. So these differences are the only Newton's divided differences, which we want to just transform as the forward differences. So which is our goal, just to write this polynomial by using the forward difference formulas. So now we go back. So this polynomial is actually is rewritten here because it has been also discussed in the equation 5.14. So now it's the same polynomial. And this polynomial can be written as in the form of sum, using sum, because so we can separate this f of x naught from the other terms. F of x naught plus f of x naught x1 into x minus x naught plus f of x naught x1 x2 x minus x naught into x minus x1 plus so on f of x naught x1 x2 so on xn x minus x naught, so on x minus x n minus 1. So these terms can be written as the form of sums. So using the summation. So next, here we can introduce this forward difference to make a simplified form of this Newton's interpolating polynomial. So Newton's divided difference interpolating polynomial can be expressed as given below: f of x naught plus delta f of x naught over h, x minus x naught plus delta square f of x naught over 2 factorial h square, x minus x naught into x minus x1 plus delta cube f of x naught over 3 factorial h cube, x minus x naught into x minus x naught 1 into x minus x2 plus so on, plus delta n f of x naught over n factorial h n x minus x naught into x minus x1 so on x minus x n minus 1. So polynomial 5.20 is called Newton's forward difference interpolating polynomial. It can be written also in a simplified form when nodes are arranged consecutively with equal spacing. So this polynomial is further can be written in the more simplified form if the given points on the x-axis have equal distance, like an arithmetic progression. The difference between two consecutive numbers should be the same. So assume that for any real number r, x minus x naught over h is equal to r. So then this polynomial can be written as, because here x minus x naught can be replaced with rh. So if we replace this x minus x naught with rh, this h will be cancelled with h and we are left with r. So f of x naught plus r delta f of x naught plus r into r minus 1 delta square f of x naught over 2 factorial plus r into r minus 1 into r minus 2 delta cube f of x naught over 3 factorial plus so on. So r into r minus 1 into r minus 2 so on r minus n minus 1 delta n f of x1 naught over n factorial. So here we make a use of binomial coefficient, because a binomial coefficient of rk can be written as r into r minus 1, r minus 2, so on r minus k plus 1 over k factorial. So this polynomial 5.21 can be written as Pn of x is equal to f of x naught plus summation rk delta k f of x naught. So just observe the difference. So this polynomial is simpler form than Newton's interpolating polynomial using the divided differences. Okay, and what if we make the comparison of Lagrange's interpolating polynomial with Newton's interpolating polynomial? The Lagrange's interpolating polynomial avoids to use divided differences, but it depends on the user. Some users like Newton's interpolating polynomial, but the others may like this Lagrange's interpolating polynomials. So, but this form is the very attractive and simpler form. Just you need to use this binomial coefficients. Okay, next we make use of this example to illustrate how it works. So example is evaluate f of 15 using given data. So for x equal to 10, f of x is equal to 46. For x equal to 20, f of x equal to 66. For x equal to 30, f of x equal to 81. For 40, 93. For 50, 101. And what is the consecutive difference between the consecutive numbers on x-axis? are just for the domain. So 20 minus 10, 10, 30 minus 20, 10, 40 minus 30, 10, 50 minus 40, 10. So here we can easily take the value of h is equal to 10. So now we need to construct a forward difference table as given below. So for x is equal to 10, this value is given 46. It can be written as f of x, or we can also write as a y, the value of y, and then 66, and then 81,
यार क्यों चौगा मारा
81, then 93, and then 101. So this second order forward difference can be computed as second. So this is the first order divided difference, which can be calculated as thus 101 minus 93 is equal to 8. Okay. And then 93 minus 81 is equal to 12. And then 81 minus 66 is 15. 66 minus 46 equal to 20. And for this second order divided difference, forward difference, we can calculate as 8 minus 12 minus 4, 12 minus 15 minus 3, 15 minus 20 minus 5. And for third order forward difference, minus 4 minus 3, this minus 1 minus 3 minus 5, 2. And then this fourth order forward difference, minus 1 minus 2 equal to minus 3. Here we have x naught is equal to 10, y naught equal to 46, delta y naught equal to 20. So 10, 46, 20, then second order difference minus 5, then third order 2, and then fourth order minus 3. Okay, let y15 be the value of y when x is equal to 15. Then we can write x minus x naught over h. We want to calculate the value of r. So it is 15 minus 10 over 10 is equal to 0.5. So here we have calculated actually r. And now just see this polynomial. It is written in the form of Pn of x, f of x naught plus r, delta f of x naught plus r into r minus 1, delta square f of x naught. We just has to replace the value of r. So replace the value of r, we will have this 46 plus 0.5 into 20, zero point 0.5 into zero point 0.5 minus 1 over 2, zero point 0.5 into zero point 0.5 minus 1, zero point 0.5 minus 2 over 6, zero point 0.5 into zero point 0.5 minus 1, zero point 0.5 minus 2. And when we simplified it, we will have finally the value of F15 is equal to 56.8672. So that is the outcome by using this Newton's forward difference interpolating polynomial. In the next example, so just observe that find the number of students who have obtained less than 45 marks. Use the following table. So in this table, actually the data is given that if the students, 31 students have marks in between 30 and 40, and 42 students have marked in between 40 and 50, and 51 students have 50 to 60, 35 students have 60 to 70, and 31 students have marks 70 to 80. So how we can calculate this? Find the number of students who have obtained less than 45 marks. So for this, we need to proceed as we will construct this forward differences. So difference table can be calculated as for x is equal to 40, we have f of x equal to 31. for x equal to 50, 42, x equal to 60, 51, for 70, 35, for 80, 31. And here again the first forward difference can be calculated as 31 minus 35 minus 4, 35 minus 51 equal minus 16, 51 minus 42, 9, and 42 minus 31, 11. So then second forward difference can be computed as minus 4 minus 16, 12, minus 16 minus 9 minus 25, 9 minus 11 minus 2. So, and then the third order forward difference can be computed as 12 minus 25, 37, minus 25 minus 2. So it will be plus 2 minus 23. And finally, for the fourth order forward difference, will add these two terms, that is 37 minus minus 23. It will be added as a 60. For any real number r, x minus x naught over h can be written as r. So here the value of h is 10 because 50 minus 40, 10, 60 minus 50, 10. So these are equal spaced data, and the difference between two consecutive numbers is 10. So that's why we can write as 10 and 45 minus 40. The 45 is the value which we need to obtain. So minus 40 over 10 is equal to 0.5. So then here we can apply the polynomial forward difference interpolating polynomial r into delta f of x naught plus r into r minus 1. And since r is equal to 0.5, so here we make substitution of this 0.5, and finally we will have p4 of x is equal to 32.997 equal to approximately we can write as 33. So 33 students which can have marks less than 45. So that is the solution. Similarly, the next example is find a polynomial whose values coincide with the polynomial y is equal to x4 at x is equal to 0, 1, 2. So again, if you we need to construct a table. So for the values of x 0, 1, 2, we have 0, 1, 16, because if you substitute 1 here, 1 power 4 equal to 1, but 2 power 4 is equal to 16. And for the forward difference, 16 minus 1, 15, 1 minus 0, 1, 15 minus 1, 14. Okay, so since h is equal to 1, because the difference between two consecutive numbers, consecutive nodes or values of x is 1. So that is why, so h is equal to 1. Therefore, for any real number r, x minus x naught over h is equal to r. And here, because the value of h is 1, so that is why we can write this r is equal to x. So required polynomial can be constructed by only replacing r with x. So then we will have a polynomial of quadratic polynomial 7x square minus 6x. So that is the advantages of this Newton's forward difference interpolating polynomials.